the Sustainability Management Master's Program, you're answering one simple question. Do you care about your future generation? If you care about your kids, their grandkids, then you care about sustainability. And a sustainability manager is someone who has the tools to make people understand how they can contribute towards developing a sustainable world. We have both part-time and full-time students. Our curriculum is 30 hours. Instead of thesis, we have a research project course and a seminar course which provides them with the kind of research background they will need to be successful in their job. But at the same time, sustainability is not always everything about environment. It also relates to the business. They will take a sustainable business strategies course. They will take a project management course. Most of these courses are going to be taught by industry people, the people who are doing sustainability on a daily basis as a part of their job. Any organization that has a large number of employees and has a physical infrastructure, they will have to have a sustainability office. If you have the passion to develop and maintain a sustainable world, come to us and we will help you shape your passion into a career which will create an impact.
Foundation Fellow. So now all yours, Tom. Welcome.
And hi, and it's always good to be here. Appreciate it, and great to work with Dibs and worked with Samir, who's now Dr. Samir. So I want to thank Samir for the work on the lab studies with the char. And certainly I'm very excited about the ability to get AKO enders. And I'll introduce AKO. I'll provide some introduction to the panel, to our conversation. I'm going to turn it over to the expert. But I was very excited. AKO, one of the things I'll note is he had one of the top 10 cited papers of ever, number of years ago in the area of biochars, what they're about. Each chart depends upon the biomass, but he can talk to you about that. He's worked with who we call the father of biochar, Johannes Lehmann at Cornell, who's I have to say, in terms of in AKO, I'm sure you know that better. But since I've been a student of this sort of field of biochars, particularly from the standpoint of environmental pollutant treatment, seeing where it is now in the realm of the IPCC, the climate panel, and the work of Dr. Lehman in noting it as a significant solution to what we're dealing with in terms of this climate crisis, but also the multiple benefits that it brings. And AKO also it has worked with the technology very importantly. And in fact, my partner has often sought AKO's help in pyrolysis. And so there's the whole thermochemical aspect of chars. And it was just really interesting to have a brief conversation with AKO about PFAS, which I dealt with while I was at EPA. I was also a permanent deputy director of the water program in the Mid-Atlantic. Last stint, I had worked around the country, and then acting director dealing with PFAS actively, and at this point, West Virginia, as well as Bucks County. And, public hearings where you've got parents of children with cancer, cancer clusters very much concerned. We also, at that time, issued a health advisory of 70 PPT, and it's come a long way where we're now seeing EPA just issued water quality standards at 4 PPT. And I'm going to talk a little bit about that, but I was excited to hear AKO really help to put into context the complexities of these types of chemical compounds, particularly as it relates to the complexities in understanding chars. And nothing, as we know, is black and white, but understanding that sort of the physical and the chemical aspects is what is important in terms of being able to use a char to treat something like a PFAS. So I was excited, would you please speak at this upcoming webcast, because this is such a timely topic, both for chars, for biochar, as well as for PFAS. So I'm going to just give a few introductory remarks, and then I'm going to turn it over to Akil. Thank you. So just briefly, I hate to start off as Debbie Downer, but I'm sorry. Well, it is the end of the semester, so feel good about that. But we all have this in our bodies. PFAS, these perfluoro and per and polyfluoro compounds. These are the types of applications that they've been in. You'll hear PFOA, which is nonstick firefighting foams, and then you'll hear PFOS, the two most common, most prevalent as related to the monitoring that's been done to date out there. But it's in our bodies, and there's greater concern about understanding the health effects and ramifications. But they're very pervasive, and the reason they work so well is the reason we're dealing with them today. So this was just an example where you find them. The structures of these compounds, as I mentioned before, the perfluorooctanoic is the PFOA, and the perfluorooctane sulfonic acid, which has the sulfonic group on it. Those are the ones that you'll hear, but this has been since the 1940s, and you probably heard about the movie Dark Waters, if you didn't see it, very popular movie about the attorney who became the worst nightmare, as the book was called, Worst Nightmare for DuPont, DuPont and 3M, but DuPont, which actually created these compounds. And he's won one of the most significant lawsuits on behalf of the victims in Ohio and West Virginia who were exposed to these compounds. And we continue to hear about these lawsuits, successful lawsuits. I will also say that ATSDR, which is part of Centers for Disease Control, have been, there's more money as a result of that lawsuit. As a matter of fact, it was over $670 million. There's more money continuing to do research. So you can see the types of health impacts and why it's such a serious matter. So there's a CDC website you can check out. There's also an EPA website. Waterkeeper, this was just to point out that in the balance of things, and I will say EPA put a health advisory out there because these were not regulated. They were unregulated monitored chemicals. And then all hell broke loose. I was part of that whole release. And really, it got handed to the states to deal with it. And I will say, New Jersey was one of the first, truly stepped up. New York, Michigan, and there are more states. This is the Waterkeeper. So if you've heard of Waterkeepers in your area, they're actually international. Started a citizen monitoring. I should say it wasn't really citizen. They did use very scientific protocols to collect samples around the country, and asked me to peer review this study. And I think this is the start of the ability for citizens, to be able to monitor for this chemical. And there's a company called Cycloplur that does this. They analyze 114 watersheds. And we're going to see more public-facing data like this, but you can see all the types of PFAS compounds. And Dibs, congratulations again on the big grant and the work that I know Stevens is going to be doing in this area. It's so exciting. And then if you look at the top of this chart, you'll see, if you could read that, it says PFOA, PFAS. Again, what they found, which is consistent, that those are the two most prevalent. Don't worry about this, EPA.gov. EPA now has a whole strategic plan on PFAS action. And these are the kinds of, strategic targets that EPA has. And certainly, to include and prioritize those marginalized communities who have been underrepresented, who are frontline, already bearing many other environmental insults, have poor health, so are more vulnerable, but certainly to also hold polluters accountable and to revisit permits. So I mentioned drinking water, but the National Pollutant Elimination Discharge Program, NPDS, for wastewater treatment, there's now a requirement for monitoring and analysis of anything that's going into that system and to pre-treat it before it would be discharged to waters. So I just want to point out now that's 4 parts per trillion. These are the highlight New Jersey, which came out with 13 parts per trillion after that 770 PPT advisory. So it was PFOA 14, PFAS 13. There are other parts of the country that have even lower, but the map here from Schaefer states shows which states are actually setting standards, which ones are still thinking about it. And you can see where we are. We're in the safe states. You too, Akil. I think we should see more coming along. And I'm gonna let the expert talk about biochar. Carbon rich, porous. It's carbon negative. It's negatively sequestered carbon. What I love, I've now worked with it, have a char company. I've been so excited about how to activate this. It's been so great to also partner and work with Stevens. So if any of you are interested in understanding more about it, there are a number of us around. And this engineered char is really, where we are in terms of looking at complicated compounds like PFAS and even more. But happy to say that we were able to actually activate our chars to get pretty much 99. That was with 1% activated ecochar to get more than 99% removal and absorption. Also just highlighting some of the heavy metals that we've treated, the beauty of the char. So with that, I will turn it over to you, Akil.
All right. Thanks, Dominique. Let's see if I'm capable of sharing my screen.
So I'll stop share.
And yep. Aha. I think it's working. So yeah, great. Thanks for the intro. Yeah, as you mentioned, I've been working with char far too long, since I was young. Let's not think about that. Here I am at the Cornell pyrolysis facility, a really highly over-engineered charcoal maker. I call her Trudy. She squeaks. Anyway, I organized this talk today into 3 general sections. The first is just an overview of biochar, followed by an introduction of PFAS. I hope to not be too redundant on your points there, Dominique. And then finally, an intersection of the 2, how pyrolysis biochar systems can help mitigate PFAS contamination. And I hope that I'm comprehensive yet understandable at the same time. And if all goes well, we'll have time for some questions afterwards. So fingers crossed. Here we go. Let's start with the definition of biochar as the solid product of biomass pyrolysis. And some would argue that the biomass must be waste stream material rather than purpose grown. For what it's worth, I mean, I agree with that, given just how much organic waste is already available. Some would also insist that biochar is only for soil incorporation. And I personally don't see the need to limit the scope of application as such. I think there's ample opportunity to use biochar that is unsuitable for agricultural purposes, potentially because it's got too high a concentration of nuisance metals like copper, to displace carbon-intensive materials like in concrete or plastics. And likely, the most well-known example of biochar that you would know is charcoal. However, there is a distinction here. being that charcoal is intended as a cooking fuel and so is consumed. Biochar, on the other hand, is intended to be conserved so that we can make the best use of its unique physical and chemical properties. Woo-hoo-hoo. So onto biomass. When I refer to biomass, I mean the residue of all living things, being both plant and animal, which that is a giant category. We can parse this into primary and secondary biomasses. Primary things like corn stover or rice husk, nutshells, other food processing residues like butchery waste, forestry slash from diseased trees, and so on. And then there's the secondary biomass like manure, biosolids, cake, paper mill waste, and even tire rubber, although some of these can be agriculturally problematic. But really what it comes down to is carbon content, because that's where the magic of pyrolysis happens. And by and large, plant biomass is the most ideal because of its high lignin and cellulose content and its inherent physical structure and a general lack of toxic things. And okay, another definition onto pyrolysis. Pyrolysis is a thermochemical conversion process like gasification or combustion or hydrothermal carbonization. Thermochemical simply meaning that heat is used to convert chemical composition. And for pyrolysis, we're generally talking temperatures in the range of 300 to 600 degrees Celsius, possibly up to 900 degrees Celsius. And technically speaking, pyrolysis requires a complete absence of oxygen, which guarantees that none of the carbon is sacrificed to produce heat. You could think of that as the opposite of combustion, where biomass plus heat plus oxygen, you're left with a pile of ash. That's all you get. But in reality, anywhere in between these two extremes will produce char. So, and yeah, in addition to the solid biochar product, there's also the liquid product referred to as bio-oil, and the gaseous product, which is primarily carbon dioxide, with some amount of carbon monoxide and hydrogen and methane as energy carriers. And so, yeah, basically, you get the biomass hot, keep the oxygen away, and simple as that. But of course, there's a little more nuance in that the pyrolysis parameters can affect the product distribution as well as their characteristics. And for biochar, slow pyrolysis is optimal. Large feedstock particle size and lower heating rates are going to favor biochar yield and preserve the physical structure of the original biomass. Whereas fast pyrolysis is optimal for producing the bio-oil. And here, small feedstock particle size enables high heating rates, and short gas residence times ensures that the liquids are collected before they have a chance to react either with each other or with the char. And in fact, the liquids and gases evolve so fast out of the biomass particle that they basically explode, and the char that you're left with is just kind of dusty. And then there's gasification, which is optimal for producing gases. Go figure. And in the case of gasification, these are higher temperatures with some quantity of oxygen present, which limits the production of solids and liquids. And generally speaking, the higher temperatures benefit carbon concentration, carbon stability, and surface area, but the trade-off is that you sacrifice yield. And overall, biochar characteristics, under slow pyrolysis conditions, roughly 50% of the carbon is going to be present in the char product. And all the inorganics, like plant nutrients, they remain in the solid phase, and so they become concentrated. And most notably, the carbon-carbon single bonds become carbon-carbon double bonds, organized in ring structures, And this is called aromatic carbon, which is noteworthy because the higher bond energy translates into a greater resistance to abiotic or chemical decomposition. And beyond that, microbes don't have the enzymes to use aromatic carbon as food. So that means that the biochar resists biotic decomposition as well. And then finally, the electron arrangement of aromatic carbon is such that there's this delocalized electron cloud, which makes the biochar electrochemically active or sticky. And what we have here, I took that picture on the bottom, pretty happy with that. So here we're highlighting the innate pore structure of biomass. And what you see are the macro and mesopores, which provide a nice cozy habitat for microbes and plant root hairs and so on. But beyond that, there are some post-processing techniques that can enhance both the quantity of these pores and these surfaces, and also the chemical properties of these surfaces. And these processes I'm referring to are activation, doping, and what I call decorating or fortifying. Activation requires temperatures really high, over 850 C for hours, up to days, which is to say that it's a very energy intensive process. We can parse this even further into physical and chemical activation. Physical activation uses steam or carbon dioxide as the activating agent. And characteristically, steam will enlarge all existing pores to result in a wider pore size distribution. But if you take it too far, the steam activation can actually eat up all of the micropores. And then there's CO2, which both creates and widens pores. And so you can really get a bump in microporosity using CO2 activation. And then there's chemical activation, which entails mixing chemical activating agents like potassium hydroxide, potassium permanganate, or zinc chloride, either mixed with feedstock prior to pyrolysis or mixed with the biochar prior to a post-pyrolysis heat treatment. Chemical activation is notable for creating extensive pore networks, kind of like, think of it like a river network, brooks into streams, into tributaries, into larger rivers, which enhances transport of pollutants into the micropores. Onto doping, where this is where other elements are mixed, right? You're mixing things with the char and then you're cooking them. They become chemically bound inside the chemical structure of the char. And the point with doping is to create charge and balance. And lastly, this decorating, which is when elements or substances they're closely associated with the char, but they're not chemically bound to it. Basically, the biochar is being used as a highly porous scaffold. And the point of all this is that biochar is not a singular material, but a range of materials whose physical and chemical properties depend both on what it's made from and how it's made. So why do we care? Well, let me illustrate this with the example of dairy manure biochar. So compared to the dairy manure feedstock, the biochar product is dry, deodorized, sterilized, stable for storage, and with reduced transportation burden and simplified application. And the carbon in the dairy manure biochar will persist for tens to hundreds of years, where it will be able to improve soil fertility far longer than the manure from which it came. The pyrolysis heat treatment concentrates the plant nutrients and also transforms them into a less leachable form. And in conjunction with increased nutrient retention from the biochar carbon, The dairy manure biochar can help to mitigate harmful algal blooms and eutrophic dead zones, which were really in the news a couple of years ago. And so this is an example of utilizing a waste stream material as a resource that provides carbon sequestration and in a system that can also recover what would have been lost nutrients. Most notably phosphorus. I don't know if you guys have touched on peak phosphorus, but that's a whole nother button right there. And, you know, I briefly want to mention the historical precedent for biochar because this is pretty compelling. The Terra Preta de Indio. Tropical soils are just notoriously poor because of all of the rainfall and all of the heat, which enhances weathering and creates what's basically acidic sandstone. Nothing really wants to grow in it. Doesn't hold nutrients, doesn't hold water, sets up like a brick. And up to 8,000 years ago, the Amerindians of the Amazon River Basin started incorporating manure mixed with bones and terracotta pot shards and char into their soils. And this was a very widespread activity. And these soils remain the favorite soils for farming to this day, even to the point that these soils are bagged for sale. So that would end my little biochar section. Feeling nice and fuzzy, let's step into the PFAS and get depressed. Hope to not be duplicating too many of your frightening factoids here. What's there to say? 2009 Stockholm Convention listed PFOA, one of the more widely produced PFAS compounds, under Annex A, its top tier of persistent organic pollutants. And PFOS, a close relative, is listed under Annex B, right alongside DDT. Pretty serious business. 2015 survey by the National Health and Nutrition Examination Survey, released by the CDC, found that PFAS were detectable at 98% of Americans' bloodstreams, and that levels were high enough to be of concern in 95% of those samples. Big deal. The concern over PFAS arises from health effects. Excuse me. I lost my place in my notes. Health effects including kidney and liver damage, possibly cancer, immunosuppression, immunotoxicity, metabolic effects including diabetes, obesity, heart disease, endocrine effects including thyroid downregulation and accelerated puberty. And you know, the piece that I had was 70 ppT, the US EPA lifetime health advisory limit, which is now 4 ppT. Didn't have the chance to do the math, but already at 70 ppT, this is 4,600 times the limit for lead. Let's see. Yeah, PFAS first produced in the 1940s, and they are everywhere. Better living through chemistry? I think not. Present in consumer products ranging from water repellents. Does DWR, durable water repellency, ring a bell for anybody? It's all over my outdoor gear, super frightening. Waterproof mascara and eyeliner, sunscreen, other cosmetics like shampoo, shaving cream, nonstick products like cookware and dental floss, stain-resistant coatings. We all know Scotchgard, don't we? Oil-resistant food packaging like microwave popcorn bags, fast food takeout containers, paints, waxes. Industrial products like pesticides and herbicides where they're used as spreader stickers, and surfactants in chemical processes, and so on and so on. And probably the biggest offender are the aqueous firefighting foams, the AFFFs. Essentially, these are bubbles that spread really well and don't burn. And this chemical stability also means that PFAS are practically non-biodegradable and persist for decades. So coupled with widespread use, these characteristics of high mobility and high chemical stability have led to ubiquity in the environment. They were even found in the bloodstreams of Arctic wildlife up to 20 years ago. More definitions. Per and polyfluoroalkyl substances are a class of some 5,000 to 10,000 synthetic compounds. Per meaning complete fluorine substitution, and poly meaning at least one. Fluoro refers to the element fluorine, right above its highly reactive cousin chlorine on the periodic table. And alkyl substances, which are single bonded carbon chains, typically 4 to 14 carbons long. PFAS are organized into fluorinated polymers like Teflon, fluorotelomers, which the polymers are made from, and the perfluoroalkyl acids, like PFOA and PFOS, collectively PFAAs or PFAS. And these are the end decomposition product of the polymers and telomers, and also are the most mobile in the environment. And so these are the focus of remediation efforts. And here's one example. This is PFOS, perfluorooctane sulfonic acid, meaning a fully substituted 8 carbon long with a sulfonate functional group. The PFAS structure is defined by an acidic functionality on one end and a carbon chain tail. The tail is hydrophobic while the head is hydrophilic, which means that these things are not soluble in water, they're not soluble in oil, but they mix with both, which makes them ideal surfactants, and also highly mobile in the environment. The high electronegativity of fluorine makes the carbon fluoride bond the strongest bond in organic chemistry, which also envelops that chartreuse, or whatever color you want to call that, envelops the tail in an electron cloud that prevents it from chemical attack. And the specific chemical properties of a single PFAA depend both on the composition of the head and tail, and like biochars, PFAAs are quite a wide range of materials themselves. And on to mitigation. So PFAA mitigation with biochar pyrolysis systems can focus on either immobilization or decomposition. Now, with regard to immobilization, it's critical to prevent the spread of this stuff, and that's where biochar comes in as an adsorbent. But it's important to note that this adsorption, it does not decompose the PFAS. It's still there. It just prevents it from spreading. From a practical perspective, it's most important to target PFAA sources like landfill and wastewater treatment plants, landfill runoff and wastewater treatment plants, agricultural fields where biosolids were used as fertilizer, and Air Force and firefighting training sites where large quantities of aqueous firefighting foams were regularly dispensed in training exercises. And let's see, so, two possible ways of getting at this. When biochar is used as a filter material, for instance, in water, it can be recovered along with adsorbed PFAAs, which can then be dealt with. However, when biochar is soil incorporated, the longevity of the biochar then becomes very important, because as soon as the char is not holding onto the PFAAs anymore, there they go. And let's see, we've got 3 mechanisms by which the biochar is able to adsorb or capture these PFAAs. We've got the hydrophobic interaction, and this is like attracts like with regards to hydrophobic and hydrophilic structures. Electrostatic attraction, and this is the opposites attract piece, where the negatively charged head of the PFAA molecule is attracted to positively charged biochar functionalities. And then there's physisorption, which is enabled by close contact between the electron cloud of the PFAA tail and the delocalized biochar electrons, especially in tight spaces like micropores. To expand on each of these, hydrophobic interactions are due to both repulsion between the nonpolar hydrophobic tail of the PFAA molecule and the surrounding water molecules, and the attraction of the hydrophobic tails both to each other and to hydrophobic biochar surfaces. Basically, entropy states that your salad dressing will separate. And this process starts with the PFAS molecules on the biochar surface, and then once you're past a certain concentration threshold, the molecules self-assemble into these mycels, these toxic little oil bubbles. And as regards biochar properties, biochar hydrophobicity will increase with increasing pyrolysis temperatures and residence times, which create a biochar that is more purely this double bonded aromatic carbon. And the extent to which PFAS are prone to hydrophobic interaction increases with the length of the fluorinated hydrophobic tail, as this nonpolar section then predominates chemistry over the polar head. Electrostatic attraction, next up. This dominates for the short chain PFAAs due to reduced hydrophobic masking from the tail. And the PFAA head will be negatively charged when the acid group deprotonates, and this happens in the majority of environmental matrices. And so positively charged biochar surfaces or positively charged intermediaries benefit that effect. Unfortunately, biochar surfaces are usually negatively charged. And in this case, repulsion will dominate for short chain PFAAs, but could be overcome by hydrophobic interactions for the longer chain PFAAs. And let's see, finally, physisorption. This is what activated carbon and to some extent biochar is notable for. This is a reversible process which permits regeneration, which is great, but it's also non-selective. And the point that I'm trying to make is that soil organic matter can compete for adsorption sites with PFAAs. And furthermore, pore blockage with clays and silt particles in soil environments can also interfere with PFAA capture. And so, yeah, to top it all off, soil is also a range of materials. And I'll mention that when I was putting this presentation together originally for the IBI, trying to, weed through the papers, it made my head spin. Because you have a whole bunch of conflicting results, and you need to, the trick is to figure out why. And okay, and then there's decomposition. And so immobilization, decomposition. PFAS decomposition temperatures are affected by the chain length. The longer they are, the higher the decomposition temperature. It's also affected by the acid group involved. And the top panel here shows you decomposition curves for PFOA and PFOS. They're both 8 carbons long, but totally different shapes, owing entirely to the acid functionality. So, yep. And promoted by the presence of oxygen, which promotes decomposition. If oxygen's not present, the primary pathway requires hydrogen, easily produced by cracking steam. And this is the current practice for decomposing PCBs, actually. And beyond that, pyrolysis is customarily used to regenerate somewhat costly activated carbons without destroying them in the process. And so the removal and destruction of PFAS can be treated as a 2-step process. An initial pyrolytic step at temperatures potentially as low as 450 C over long periods of time, followed by combustion of the evolved gases at higher temperatures. But go figure, the world is a complicated place and conflicting evidence abounds. I know of one example. There's at least one pyrolysis technology manufacturer that claims complete removal of PFAS from sewage sludge, and at least one author that's noted only 50% reduction from lengthy pyrolysis at 700 degrees. It's complicated. Sewage sludge is a mess. What else is in there? There's some talk of calcium and sodium salts to promote decomposition. But in either case, and this is very important, the smokestack emissions are a special concern. Incomplete decomposition of PFAS can produce carbon tetrafluoride and hexafluoroethane, and these are both potent greenhouse gases with a global warming potential something like 7,400 and 1,200 times that of CO2, with lifespans of 10 to 50,000 years. Basically, once it's in the environment, it is there forever. So the bottom line here is that there's a bunch more work that needs to be done to guarantee both elimination of the different types of PFAS from various feedstocks during pyrolysis, as well as complete destruction during thermal decomposition. And on that note, I will thank you for your attention. I hope your brains are totally full. Happy to answer any questions.
Wow.
Speaking of a downer, at